Section 6.2, Future Value of an Income Stream. This is going to be a really instructive, helpful section because I want to frame this whole section around a concept and a reality that I think is super important to everybody in this class: retirement. So the idea is you don't want to work forever. At a certain point, you want to be able to kick back and hopefully live off of income from investments. So as you're going through your working career, you can put away, and save, not just save, but actually invest and earn some interest on a portion of your income. And the goal is, over the course of your career, you put away into investment accounts and different sort of retirement vehicles enough money so that by the time you reach retirement age, somewhere between 62 and 72 years old, let's say, there'll be enough money in those accounts to where you can just live off of the interest. Because if the principal balance is large enough in your retirement accounts and you're receiving some amount of interest, say, somewhere between 5 and 10%, you could be able to just live off of that income and not have to work anymore, right? So that's the goal. In this section, we're going to be exploring the math and the formula that helps us determine, how much we'll have at retirement. We could calculate this for ourselves or for anybody. We could also do calculations about how much do I have to save? How much do I have to put away each month if I want to retire with X amount of dollars at age Y? So this is very, very essential, important math. And I'm happy that we're doing this because, not only are we going to learn about how integration applies to this type of thing, we can also be more informed making decisions about how we're going to save our money as we enter our careers. So let's start off with an annuity, just defining this. An annuity is a special type of income flow in which payments are made or received at regular time intervals over a specified term. Okay, so maybe you've been putting away money, or you have an actual annuity which is provided by an insurance company where you put away a certain amount of money per month, and then in retirement, say at age 65, you start withdrawing and you're going to have regular payments coming your way, which you can live off of. All right, the future value of an income stream, we're right here, over a specified term is the total amount, that's the money transferred into an account plus interest that is accumulated during the term. Okay, so here is the actual definition and the integral that we'll use to evaluate this. Future value of an income stream. Suppose money is being transferred continuously into an account over a time period 0 to capital T. So capital T we're going to use as the length of the term. Okay, and we're doing this at an annual rate. This is important. Determined by the function f of t. So f of t is the rate at which we are putting away money. So this is like the saving function. How much are we saving per year? If the account also earns interest at an annual rate of r, compounded continuously, then the future value of the income stream over the term t is given by the following integral. So here it is, future value. It's the integral from 0 to capital T, that's the length of the term, of f of t, that's our savings rate, times e to the r, big T minus little t, dt. Okay, so for these problems, t is going to be an actual number, like this is going to be a constant value, a predetermined length of the term. Lowercase t is going to be the variable. Okay, so we're going to be integrating with respect to lowercase t. Okay, and then this is just another way to express this integral, e to the r capital T. I know it looks like these are 3 variables here, but actually these aren't. E is just Euler's number, approximately 2.72. R is going to be our interest rate, which will be predetermined, and T, capital T, this is going to be a fixed number. So this can be pulled on the outside of the integral. All right, so just another way of expressing it. Now, let's look at an example, kind of bring all this back down to earth here. Let's look at this. At age 25, Tim starts making monthly deposits of $200 into an IRA account, which is a type of tax-advantaged retirement account. Oftentimes, people will use this. I would recommend it. And it pays an interest at an annual rate of 7% compounded continuously. Assuming that his payments are made as a continuous income flow, how much money will be left in his account when he retires at the age of 60? And after that, we'll look at what if he waits 5 more years and retires at age 65. All right, so kind of a lot to pick apart here, but let's get into this. We are going to be using this formula because we're ultimately being asked, like, how much money will be left in the account? What's the future value? That's what we're being asked for. Okay, so this is equal to the integral from 0 to capital T, f of t e to the r times capital T minus t dt. I have the habit of writing down formulas. Every time I use them, that's how I remember them. I write them down a lot. Okay, so what do we have? Like, what do we know from this formula? I guess we kind of go left to right. Like, what about capital T? Let's see if we could figure out what we have for this. So capital T, this is the length of the term. And we can calculate in this case, like, okay, for how long, for how many years will Tim be making monthly deposits? Well, he's 25 now, and let's say we're starting out by thinking, if he retires at age 60. The length of that term is just going to be the final age, which is 60, minus the starting age, which is 25, which gives us 35. All right, so T, capital T in this case, it's going to be 35 years. Let's keep going. How about f of t? What is our savings rate going to be? And remember, this is an annual savings rate. Well, he's saving $200 per month, right? So just multiply that by 12, and that will give you the annual savings rate. So 200 times 12 months, we'll have $2,400 per year. Okay, so this is just to include units. This is years. This is dollars per year. Okay, let's keep going. How about R? This is our rate of return, annual rate of return, in this case, 7%. 7%, remember that percent is per 100, so that's just, divide by 100. So 0.07 will be the decimal form of that rate, and that's what we're going to want to use here. Okay, and that is everything that we need because t, lowercase t, is going to be our variable. So let's set up our integral and find the future value. I don't know why I put ft here. F v future value will be the integral from 0 to 35. And in for f of t, our savings rate will be $2,400. All right, that's how much we're putting away per year continuously, times e to the 0.07 times capital T, which is 35, minus lowercase t dt. So there we have it. That's the setup for the integral. Now let's evaluate this. And the output of this is going to be the amount of money that's in the account when he retires at age 60. So let's start working through this. First, I might pull the 2400 on the outside of the integral, right? Like if there's anything that isn't expressed in terms of lowercase t, it doesn't have to be inside of the integral. So it'd be a good idea to get that out of the way. I can simplify this a little bit. So I'll write this as e to the 0.07 times 35 minus 0.07 t. So what I did is just distributed the 0.07. And I'm doing this because now I can break up, this thing right here to e to the 0.0735 times e to the negative 0.07 t dt. And I do this because this now is just some number, right? This is just going to be a constant value. I can pull it to the outside of the integral. And I'm doing all this work to make it easier for myself to evaluate the integral at the end. Oops, sorry, I want to write that. E to the 0.07 times 35. And now I'm just integrating from 0 to 35, e to the negative 0.07 t dt. So what we've done is we've essentially taken it out of this form and put it into this form. Okay, just pulling all of that on the outside there. Okay, and we even pulled out our f of t actually because that was just a constant value, right? The rate of savings was constant. Now I just want to evaluate the integral and simplify. So, okay, we have all this stuff over here. I'm just going to focus on the integral for a second. Let's take the antiderivative of e to the negative 0.07 t. So to do that, we actually have a rule for this. It's e to the negative 0.07 t divided by negative 0.07. Okay, and you could check that by taking a derivative, but this is what we're going to get. And we're evaluating this from 0 to 35. Okay, so we still have all this, the 2400 e to the, all that stuff. And now evaluating this at 35. And subtract from it, evaluated at 0, so that would just be e to the 0, which is just 1. Okay, and we could simplify this at a certain point. Once it gets manageable enough to where I can turn to my calculator, I'll do that, and I'll type that in. And here is what I got. I got $363,029. Okay, so looking back, so this is what happens over the course of the 35 years where Tim is saving his money, just putting away $200 per month. By retirement, there is Yeah, over $363,000 in that account. Now here's the fun part. What if we didn't have this money invested and, Tim was just putting this in a checking account, right? So it wasn't invested, it wasn't earning this 7% continuously compounded interest. I just want to say something about this. So I'll say compare with if we just saved the $2,400 per year for 35 years. If we multiply those two numbers together, so $2,400 annual savings for 35 years, it is only $84,000. $84,000 compared with $363,029. Okay, so the vast majority of this money that's in this retirement account at retirement comes from the interest earned on the balance. Okay, this is why we invest through our entire careers, even if it's just a little bit of money, $200 per month, whatever you can do in the long term with compounding interest has a massive effect on your net worth. So if there's one lesson other than how to apply this integral that I give you in this lecture, invest your money. Okay, but we're not done. And I didn't leave myself a whole lot of room, so I'll work right here. We also wanted to look at this for, what if we waited until age 65? Okay, so let's try the same setup, same integral, same interest, everything. We're just going to change the term. Okay, so capital T, if we're looking at age 65, at age 65, the only thing that's going to change is capital T is going to be 65 minus 25. So we'll have 40 as the length of the term. Everything else will stay the same though. So the future value will be the integral from 0 to 40 of 2400 e to the 0.07 times 40 minus t dt. Okay, and the work is going to look very, very similar, but we're going to have this. So 2400 e to the 0.07 times 40. And then, the antiderivative is going to look like this. E to the negative 0.07 t divided by negative 0.07. And then we'll have different limits of integration. It's going to go from 0 to 40. Okay, and I'll spare you the details. Here is what we end up with. We're left with $529,531. That is a very significant increase just over, the course of another 5 years of saving and not spending out of this retirement account. Okay, so the magic and mystery of compounding interest. Invest your money, folks. All right, that's all we wanted for example 1. Let's look at another one. Still exploring the same topic of retirement savings, but this time we're setting it up a little differently. For this one, we're aiming for a certain future value, right? Suppose we want to have $2 million for retirement in 42 years. Your account earns 10% interest, which, by the way, is not far off from the S&P 500, historical returns I think are around 10.5%, which is a very, very popular and stable, I would say, stable-ish investment vehicle that people have access to. Okay, and that's compounded continuously. The question here is, how much would you need to deposit into the account each month in order to reach that goal of a future value of $2 million? So we're going to use the same formula here. Future value is equal to integral from 0 to capital T, f of t, e to the r, capital T minus t dt. All right, and for this one, what do we know? So we know that the future value is equal to 2 million. All right, T, our term, capital T, is 42 years. And the interest rate is given to us at 10%, which as a decimal is just 0.1. Right. And what we want to find is we want to know how much we need to deposit each month. So remember, f of t is the annual savings rate. And we want the monthly savings rate. And the monthly savings rate will be the annual rate divided by 12. So really what we're looking for is f of t divided by 12. All right, so let's set up an equation here, because we know that the future value should be 2 million. So I'll put 2 million on this side of the equation. Is that the correct number of zeros? Yeah. This will be equal to the integral from 0 to 42 of, and for f of t, this is going to be a constant rate. Like we're looking for, just the constant amount that we'd want to deposit each month. So how about I just call f of t d? Okay, and that's just for, the deposit, I guess. Okay, so I'm going to put a d right there, and that's what we'll be looking for in this problem. Okay, but everything else, e to the 0.1, and then 42 minus t dt. All right, and we can work on evaluating this integral now. And the first thing I'm going to do is I'm going to pull out d, because like we said, this is going to be a constant value. It's not going to be in terms of t, so I can pull that on the outside. Won't affect the integral. I'll pull out the e to the 0.1 times 42, just get that out of the way. And then I'll have this integral from 0 to 42 of e to the negative 0.1 t dt. And we can evaluate that, find that antiderivative, and maybe I'll just write this as 4.2, right? Just multiplying 0.1 times 42. Antiderivative, I'll get e to the negative 0.1 t over negative 0.1. And we're evaluating from 0 to 42. right, substituting in. And remember, we have 2 million on this side of the equation, so what I'm doing now is simplifying down the right-hand side down to a reasonable expression where I can then divide both sides by whatever is not d to get d isolated and get it in my calculator. So, I have the e to the 4.2. I could pull out that negative 0.1, and then I'll just have e to the negative 4.2 minus e to the 0, which is just 1. Equal to 2 million. Okay, and then from here, I think it would be reasonable to start isolating d, so I on this side would have the 2 million, multiply both sides by negative 0.1. I would divide both sides by e to the 4.2 times e to the negative 4.2 minus 1. And I put this all into my calculator very carefully, being careful with my parentheses, make sure that your calculator knows this stuff is in the numerator, this stuff is in the denominator. And I ended up with $3,044.77. This is the annual savings rate. But what I was asked for in this problem was how much do I have to save per month? Okay, so I'll just say to reach $2 million, we'll want to save, so $3,044.77 divided by 12, right? Because that's the annual saving rate. So the monthly saving rate, I'm getting $253.73. I rounded that per month. And that is our answer here. All right, it seems like a bit of a miracle, right? That if you have 42 years to retire, which I think probably many people in this class might, right? Like if you're 20 years old and you wanted to retire at 62 years old with a whopping $2 million in savings, 10% interest is totally achievable, right? A lot of the major indices return this amount roughly, right? Or historical returns are around 10%. So for a mere $254 per month, if you can manage to save that much through your entire career, which by the way, might seem like, a chunk of money right now, but with inflation and everything down the line, it's going to feel like less and less money every single year. So like this is a constant savings rate, right? Like even when you're 60 years old, you're only going to be having to save $253 per month, which is going to be like nothing then. Okay, so saving that amount and investing, you can reach 2 million by the time you retire. Okay, well, that's all that I wanted to talk about for this section. Applying this integral, finding future value. That is it for this. Next up, we're going to look at some logarithmic and exponential functions with other bases. That's 6.3. I'll see you there.